Okay, so what I'd like to now talk about is we're getting, I wanted to go through it. This is now chapter 5 in the book, which is on statistics. And I wanted us to go through over the next couple of classes some of the very, very basics about statistics. Again, one definition I heard of what a data scientist is it someone who knows more statistics than a computer scientist and more computer science than a statistician. And in order, therefore, to be a computer scientist, you need to know a little bit of statistics, and we're going to at least try to do a little of that now. Any questions? Okay. So if you want to think about what the way statisticians sort of view their world, which is, going to be a little relevant to what we're doing today, and probably more so to what we'll do on Friday. But basically, there is an underlying world of examples out there. That's what we call a population. You are generally, in the course of an experiment or a data collection procedure, getting a sample of some of them, okay? Hopefully at random, but by some kind of a sample of them. And then there's two kind of things you can kind of do with the sample. One is you can look at the sample to get properties of the sample, so you understand what the, what's there. That's usually what they mean by descriptive statistics. That's visualization, that's mean, that's variance. The other question that you would like to do is to infer something about the population. You'd like to be able to say something broader about the whole population from looking at your sample. Again, if we think about it in the context of political polling, what happens? You sample a certain number of voters. You analyze them and you find out how many of them are going to vote for each of the candidates. Why are you doing that? It's not that you really care about the opinions of what these voters are going to do. It's because you're interested in how well they reflect back to the underlying population. And so what we're going to talk about when we talk about, over the next couple of classes a little bit is what are some of the distributions that come up in the course of, statistical reasoning. And then later, how do we infer whether or not, somehow what we observe in the sample is likely going to hold for another population. Any questions? So that's the basic big vision. But today what I'd like to do is just talk about basically 4 different distributions. That is my goal for today. And whenever you observe a random variable, or you observe features of something, you get some stream of numbers for something, they should be coming in some kind of a distribution. And what kind of the neat thing is that there's a relatively small number of famous distributions that fit a lot of the patterns that the frequency distributions that data tends to come in. And so it's kind of important to understand what these distributions are and to feel comfortable talking about them. Any questions? And if we think about what is good about knowing about these classical distributions, there's a couple of different reasons why we're going to care about it. On one level, if I give you data, it's just data, and you analyze it, and you play with it, and you look at it. What knowing about whether your data fits a classical distribution, you get a couple of things sort of for free if you know what distribution it's from. First of all, many of the classical distributions usually have sort of reasons why they arise. And so if your data sort of fits a power law, there is something that you probably know about what's generating your data that is interesting to know about. If you have, know that your data comes from a particular distribution, there's often closed forms of things, certain statistical things you'd like to know, like what is the variance of my data or stuff like that, that would kind of pop out from that classical distribution. The warning I'm going to give is that just because data looks like it comes from a particular shape doesn't mean it necessarily comes from a particular distribution. Okay? But I still find it very, very useful to look at a data set and figure out which, when you look at a frequency distribution, what is it causing it? Okay? Any questions? Okay, so the first distribution is something that you're presumably all familiar with, which is a binomial distribution. And in a binomial distribution, you've got data that's coming from a bunch of independent trials where there are two possible outcomes. Okay, a coin, for example, can come up heads or tails. Okay, and what a binomial distribution is typically looking at is what is the probability that when we have n things, okay, sampled from the distribution, what is the probability exactly x of them came out heads? That's kind of what a probability is, a binomial distribution is. And in this case, there's basically two arguments to the binomial distribution. One is the probability of heads, the other of which is how many coin tosses you're going to be doing. Okay? Any questions? Now, you may remember earlier on when I was talking about variance, I talked about a example where I said that if you have a batter who is hitting, gets hits 30% of the time, which is considered to be a good batter, what is the likely percentage of hits they will have gotten over a 500-game season? Okay? And that we could see that a lot of the difference in observed performance between a batter and different years could be just due to fluctuation and randomness. What that was really saying is, if you look at it, the probability, the number of hits that a batter who would get a hit with 0.3 probability and make out with 0.7 probability, okay, the number of hits they get if they got up n equals 500 times is given by this distribution, right? And so for somebody who's a real 300 hitter, real in there, that 30% of the time they would succeed if given an infinite number of chances, this would kind of enable you to give the distributions of season. This was a binomial distribution. Any questions? Okay. So what is there about binomial distributions? Okay. Generally speaking, for coin tosses, okay, if you tossed 200 coins here, wait, no, what am I saying here? It looks like here I tossed 200 coins, okay, that were evenly distributed. This would be showing what's the probability I got exactly, x heads, okay. In general, x was the expected value of this would be p times n, that should be 200, so expected value would be 100. You see that it's symmetric. You know about that kind of thing. Any questions? Now here is also a binomial distribution. Let's say that we were going to be having a world where we had a light bulb. Okay, when you turn on a light bulb, every once in a while the light bulb burns out, right? Actually, every bulb only burns out once, but let's say that on average, every 1,000 times you turn on a light bulb, okay, or every 1,000 hours of a light bulb, it burns out, okay? What is, if we had 1,000 light bulb events, okay, what's the number of burnouts we should see? This, I claim, is also a binomial distribution. Okay, I feel I'm now talking to you guys and not interacting, so this is maybe my fault. Do people see why the light bulb model can be modeled as kind of a binomial distribution here? If you picture that for every time you switch a light bulb on, it burns out with a probability of 1 out of 1,000. Okay? You can now ask yourself, if I flip it 1,000 times, how many burnouts, what's the probability that I will get a certain number of burnouts? Okay? And this is exactly what would be modeled by a binomial distribution. Why is this distribution not bell-shaped? Okay? If it's a binomial distribution. Why is it that if I flip 1,000 bulbs, okay, why is it that I don't get a bell-shaped here?
What is the x-axis?
In this, the x-axis is the number of burnouts. Okay, the y-axis is the burnouts per 1,000. Okay, the y-axis is the probability that I had that many burnouts. If I did this experiment 1,000, times.
For this curve to be like symmetrical, would have go to the negative x-axis. one of the negative.
Does everybody see that in this case, because the probability of a burnout event is so very, very low, okay, we don't have room kind of for the symmetric part of it. Does everybody kind of see that? If I had made either this probability higher or I jacked up my number of experiments here, okay, then you would see the symmetrical part, right? You see that if I had made this 1,000,000 times, how many light bulbs would I expect to burn out if I did this experiment 1,000,000 times? It would be about 1,000. And you would see something that you would then see the other part of the distribution. Any questions about that?
How many burnouts per 1,000 per bulb?
This is how many burnouts per 1,000 events. Well, but if it burns out, I put in another light bulb, okay, or something like that, okay. So it's like a coin toss, okay. Any questions? Okay. So both of these kind of get modeled by binomial distributions. But notice, just I guess the lesson here is sometimes when you see a distribution that isn't symmetric, it's because you have sort of too small a set of things. How many people understand why this distribution is not symmetric? How many people are confused by that? Because I don't get the sense I'm connecting. Okay? Let's think, what would the distribution be if I burn, let's say I have a light bulb that every 1,000 times you turn on a light bulb, it burns out. Okay? Suppose I try this experiment 1,000,000 times. Is that 1,000,000? How many bulbs would if I tried it for n equals 1,000,000 times, how many bulbs would I expect to burn out? 1,000. Does everybody agree that at 1,000 is probably where I would get the peak probability? And what's the probability that you think that if I went to try to flip the light 1,000,000 times, none of the light bulbs burnt out? Almost zero. Okay, it's always possible that the coin could come up heads, 1,000,000 times, but that's going to tell you that with this distribution, you would get a symmetric distribution. Does everybody see that? But if I had a smaller number of these things, this distribution is going to be shifting, and because you can't have a negative number of burnouts, okay, eventually the distribution is going to run up on the edge. Does everybody see that? So that's something that when you're looking at data, when you see a distribution that's half symmetric, maybe that's a sign that you didn't run enough trials or a big enough thing, or you have to understand why. Any questions? Okay, good. Now, the other distribution that you should be familiar with, of course, is the normal distribution, which we've talked about in here, which is another bell-shaped distribution, okay, that's usually used to denote things like height, IQ, things like this. Okay? And what makes the normal interesting is it is also parameterized by two parameters, the mean and the standard deviation, or the square of the standard deviation being the variance. Okay? And it has this complicated looking formula to describe what that distribution is. That is the normal distribution. Any questions? Okay? So what are the interesting properties of normal distributions? The normal distribution is essentially the binomial distribution where n goes to infinity. Okay? So if we think about what the binomial distribution, this thing about counting how many heads and tails you have, that is something I, as a computer scientist, understand because it's discrete and I do discrete math. Okay? The normal distribution looks a little frightening with all those e's and square roots and things like that. Okay? But reality, basically, it just basically is a generalization of it where n goes to infinity. And the parameters change. Okay? Where now, instead of how many flips we have and what the probability is, instead it's parameterized by what the mean is and what the standard deviation is. Okay? And the good thing is that the normal distribution really is bell-shaped because it is defined as a function. It says it's x. X is the, what's the probability of x, the value being x? X can range from minus infinity to plus infinity, and it's continuous. So we don't have this problem of bunking up against the sides on it. Any questions about that? Okay, that should be pretty clear. Now, the other thing that is interesting is that the sum of normally distributed random variables is normal. Okay? So if you have a bunch of random variables, okay, each of which is normal, okay, the sum of them will also be normally distributed. So that would mean if we figure that, let's say, each of your homework grades in this class were normally distributed, and I now compute your average by summing them up, that would also argue that that's going to be normally distributed. Is that right? And if I add a normally distributed value to itself, that's also going to be normally distributed. So this is an argument that the linear combination of normally distributed variables should be normally distributed. Okay? Any questions about that? Yeah?
Those different variables should have the same mean. I'm thinking practically, if you are two variables, they should have the same mean.
No, I don't think it's necessary for them to have the same mean. Okay? It's still going to be normally distributed. Okay? So I don't think that's necessary. Okay. Now the most famous property of the normal distribution is that as we've said about any distribution in here, we've shown that when you have the mean and the standard deviation, they give you some tightness on the shape of a distribution. The neat thing is that because the normal distribution is completely defined by its mean and standard deviation, it gives you very, very tight bounds. Just knowing, taking data, if you know it's normally distributed, you compute its mean, you compute its sigma, you get very, very tight bounds as to where all the values are. Okay? So if we take a look at this, in a normally distributed, in a normal distribution, 68% of the data lies within one standard deviation of the mean, either 1 sigma above or 1 sigma below the mean. 95% of the data lies within 2 standard deviations of the mean. Okay? And 99.7% lies within 3 standard deviations. Normal distributions have the property that it is very, very hard to be very far from the mean in a normal distribution. Any question about that? And there's interesting implications of this. Let's just think about it. What's the average IQ in this country, in the world? 100, okay? Now the standard deviation of IQ is 15%, is 15 points. What percentage of the population is it that has an IQ above 145? Let's think about super geniuses, right? A super genius has an IQ above 145. Okay? It would be something like, by this argument, that if we look at it, 3 standard deviations outside would be bunk, bunk, bunk outside this thing. There's a total of 0.3 mass that's not within this distribution, right? What? Then half of that would be lying above and half of it would be lying below, right? So that's an argument that only 0.15% of the people have IQs greater than 145. Okay? So if any of you guys got it, you're in an elite crowd. Any questions about that? Okay? And once you assume that other things are true, again, it's the same kind of thing. I say, how many people are above 7 feet? Okay? If you know the average height in the population, and you know that it's normally distributed, and you know the standard deviation, you can start to compute things like that relatively easily. Any questions about it? Yeah.
So for any data set, for example, if I say I have a set of heights with me, I can't naturally assume that they're normally distributed, right? Like it's any set that I have of heights, if the heights in this class.
Yeah.
But can I assume they're normally going to be normally distributed, or
Okay. First of all, you can always assume whatever you want. The question is whether you're right or you're wrong. Okay? And, the way we'll talk next class about statistical tests so that you could really take a look at a sample and argue that, yes, this was probably drawn from a normal distribution. Okay? But statistical tests are sometimes, there's a dicier question. The bigger question is, are you safe in making an assumption that a group is normal? So precisely showing whether a distribution is normal, okay, would normally would require a statistical test. That much, I guess, is what I would say. Generally speaking, for a lot of things in the world, for reasoning about them on a, back of a napkin level, which is usually the way that I'm thinking about it, I would say, yes, these guys are, the class is probably normally distributed, okay? And if I knew the mean and the standard deviation, I could make some guesses about what the properties of the class would be, okay? But there's a difference between a rigorous proof that this is normally distributed and enough confidence that you can make some kind of a heuristic argument about it. And usually when I'm personally working on these things, it's usually at the level of, can I reason about it? Do I believe it's normal enough to make some kind of a statement about that? Any questions? Okay. So what's not normal? Okay, let's think a little bit, because again, a lot of distributions are kind of, you sort of would assume are normal. First, there are a lot of things in the world that look like they have bell shapes, sort of, that aren't really normal, okay? Now, a famous example has to do with stock, in the stock market, when people measure sort of day-to-day fluctuations in trading, okay? If you look at what you would call the returns, essentially how much of a change was there today versus, versus the price today versus yesterday, and normalizing that in a right way. In general, the frequency of there being an increase is roughly the same as the frequency of a corresponding decrease, okay, over a course of a day, okay? Small movements are much more frequent than large movements, so you get a bell-shaped distribution if you plot these returns on a daily basis from the stock market. Now, when you do that, however, if you compare that to a normal distribution, let me see if I can do it right. A normal distribution, a truly normal distribution, would comparatively look like this. I know my drawing is bad, okay? But the normal distribution is not quite, the distribution of returns from the stock market are not normal. They are the log of the normal distribution, which means that there's more extreme movements than you would expect from a normal distribution. From a normal distribution, if we know that things are normally distributed, we know what's the probability that there's going to be a movement 1 standard deviation away, 2 standard deviations, 3 standard deviations, 4 standard deviations away. But if you follow the stock market, crashes are rare, but they happen more often than you would expect if it was normally distributed. Okay? I don't know if what I'm saying here makes sense now. Okay? If you observe stock markets, every once in a while there is a bad crash. Okay? These bad crashes are rare events, but they're much more common than you would expect if it was normally distributed. Okay? And so things that often look normal really aren't perfectly normal. That's one argument. It may be the log normal, it may be something else. A more common exception is that mixtures of normal distributions are not normal. Okay? Let's say we take a look at the height of men. Okay? The height of men, let's say for now, is a normal distribution. Okay? The height of women is a normal distribution. The question is the height of a random person normally distributed? Okay? And this, I argue, is going to be no. Okay, and this I want people to listen to just to make sure, because this is a problem that that happens fairly often. It's reasonable, you know, we usually, we were saying in here, is height in the class normally distributed? That's kind of a natural, you know, we say that in a kind of casual way. It should be clear that even if the height, we may believe that the height of men are distributed normally and the height of women are distributed normally. But in a world where we've got a mixture of populations here, is that height going to be normal? Okay? And I think if you look at this example, you sort of see a lump in it that suggests that it probably isn't. Is that right? Let's imagine that we're more like bees, okay? If I understand, or you know, if I think about bees. Bees, if I remember correct, there is a big queen bee that is a giant thing, right? And that the distribution of height of queen bees is probably, this is the weight, the size of a queen bee. Probably looks like this. The size of worker bees may very well look like this, right? Is the sum of, assuming we have a certain fraction of queen bees and a certain fraction of worker bees, is the size of that colony going to be normal? The answer is obviously not. It's not going to have a single peak, for example, right? So if these populations were far enough away, it would be obvious that these are not normal. Is that right? So one thing to recognize is that when you have a mixture of normal distributions, the data is not going to be normally, you know, exactly normally distributed. And most things in the world probably are mixtures of populations. Do we think that the height of men is normally distributed? We agree that the height, if we agree men and women have different distributions. I think everybody agrees with that, right? Do we think that men are normally distributed? Okay, or are there some different populations of men that might be different? What would be different causes of different populations? It may be different populations. It may be that, you know, Sikhs tend to be tall, as I understand. Is that right? And it may be that for some reason that the world is a mixture of Sikhs and a mixture of other Indians and a mixture of other populations. Does everybody kind of see that? And so if we were to take, let's say, the world population, we would not expect it to be normal. What about in the United population of, let's say just Sikhs, since we now are on them? Would we expect that population to be normally distributed? If we took all the male Sikhs in the world, would that be normally distributed? You say sure. You say no. Why not? What else might be a reason why not?
How can we exactly classify height with religion? Like, we don't find out strong correlation. Like,
No. Okay, forget. I'm not saying anything about Sikhs, but I mean a particular group of people. You have everybody in the world who calls themselves Sikhs. You take their height. Okay. You can now measure. It's now a well-defined distribution. Does everybody agree? And we agree that normally we would think of this as being a normally distributed distribution. But are there still populations, different populations in there that would probably be mixed? Well, in some theoretical vision, you would kind of expect it. But I still kind of think, but there's this problem that mixtures of normal distributions are not normal is a common thing to recognize. For example, I imagine that Sikhs come in different ages, don't they? And if you plot children's populations with men, if you just take a look at all the Sikhs, okay, you would not see a perfectly should not expect to see a perfectly normal distribution, right? Because you've got a mixture of different populations there, right? Are there other situations so generally, I guess the point that I would like to make is that in general, any data set you experimentally come from often comes from a set of mixed populations, okay? And so expecting it to be perfectly normal, any observed phenomena, is probably a flawed assumption. Okay? There are statistical tests to tell whether data is drawn from a normal distribution, and we'll talk about that next class. But generally speaking, in observed data, if you observe enough data, you will see things coming from different populations. Yeah?
It's quite hard that we get exactly a distribution is quite not exactly. So if we get something like this, can we approximate it safely to a normal distribution?
So the question is this approximation good enough for a normal to be a normal? And the answer is, it depends what you're doing with that approximation. Okay? You know, if you want to use it to get some kind of a heuristic argument about, you know, how much of the mass is located at a certain space, which is usually what we use normal distributions for, you know, depending upon what you're doing, hopefully there's that level of resolution. Okay? But, you know, recognize that the normal distribution is in some sense a theoretical construct that people build. Okay? And when you see observed data, often, usually, it's a mixture of different phenomena. And so you shouldn't expect it to be perfectly normal, but a mix of things. Yeah? Is there any data set that is perfectly normally distributed? The answer would be points that are sampled theoretically from a normal distribution. Okay? So we'll talk about random sampling a little bit later. But the answer is yes. You know, when you have, you know, when you construct it from a normal distribution, okay, then I guess that is. That doesn't mean, I'm not trying to say that the normal distribution is not a useful model, but recognize that the normal distribution is usually, we treat it in the world as a model of things. Okay, and with any model, there's a point where it's true and a point where it starts to break down. Okay? And that's, I guess, the important thing that I want you to observe. You should recognize when things look like they're normal and they observe a bell-shaped curve and they pass some statistical test or look like they have the mass distributed the right way. Often we can assume that they're normal. Okay? But we should recognize that usually on some evolution, any real population is a mix of other populations. Yeah? So the sum of distributions would be your height plus weight. If I say, what is the random variable for you? It's your height plus your weight. Okay? Let's say we have that as a statistic. Right? That, I claim, is going to be normally distributed. Okay? If height is normally distributed in a population and weight is normally distributed in a population, height plus weight is going to be normally distributed. For the same person, for the same, where you're constructing a new random variable that is a sum of two different random variables, that would be normally distributed. Here the problem is you've got populations, two different normal distributions on the same, in some sense, variable. And the population of those two, I claim, are not going to be normally distributed. They're a mixture of things. Any questions? Okay? So one should be aware of these kinds of things. Any questions about the normal distribution? Okay. Another distribution that I want us to think a little bit about are lifespan distributions. Okay? So if we wanted to figure out, let's say, what, you know, what's your probability of living n days? Let's say we had a model where you have a probability of dying every day, and it's a fixed probability of dying. Okay? Let's say that I will die today with a probability of 1 out of 30,000, and I will die. You know, this is true for every 30,000 is a bad number, right? Well, if I'm going to live, how long does the average person live? Okay? What? Well, let's just say what I want to live. Let's say I want to live 100 years. So if I multiply that by 360, that's 36,000, right? So I am hoping to live about 36,000 days, right? You could imagine now, suppose the probability of me dying on a particular day was 1 in 36,000, right? we could now compute what would be the probability that I'm going to live exactly n days, okay, over the course of my life. Does everybody agree with that? And in fact, this is the distribution that would do it. For me to live to be n days means that I am going to keep breathing. I am going to live with probability, in this case it looks like 36,000 minus 1 over 36,000. That if this is my probability of living on a particular day, and this is the probability of me dying, okay, the probability I live exactly n days will be given by p living to n minus 1, because the first n minus 1 days I have to stay alive, right? And then on the nth day I finally stop breathing. Does everybody agree with that? So this is a formula that would argue that if you live in a world where failure, okay, is going to be a fixed failure in every given interval, okay, does everybody agree that this is a lifespan distribution for me? This is just like a binomial distribution, except that what's really kind of happening that I want to think about is that we're kind of, especially if you assume a world of light bulb lifespans, okay? Before we were talking about, in the binomial distribution, this thing of how many light bulb lifespans were there, how many burnouts were there per 1,000 times, right? This is another way of looking at lifespans, though. This is what is the probability of a particular lifespan happening, okay? It is the probability that there was a gap between burnouts of exactly n minus 1 days, okay? So this is clearly related to the binomial model, but the results are a little bit different, yeah? Ah, okay, so you're telling me, okay, so you're right. So it should be the problem if I don't die. You're right, so I have reversed P and 1 minus P here, right? Somebody send me mail so I can fix the slides, okay? But you're right, okay? I reversed those two. Any questions? Okay? What I'm trying to tell you here is that, that sometimes there are distributions that are better off being thought of as the gap between events rather than the number of events in an interval. Okay? Yeah.
So here we are assuming that the probability that a person will die at a particular day is like independent and identically distributed over the entire span. Is it right?
Right.
So we are assuming the same probability for each day, although in reality it might be decreasing every day.
Right. So in this case, we're assuming a fixed probability of dying on each day, not that as I get older and older, I have a better chance. Under this model, once I've hit 100 years old, I have the same probability of going for another 100 as I did the first day. Okay? That may not be what you want to model, but that's very useful to model certain things. In particular, there's the distribution called the Poisson distribution. Okay? And this is a Poisson distribution is one. Normal distribution, I always know how to think about a normal distribution. Binomial distribution, I think about that. The Poisson distribution always makes me a little nervous because it sounds like an advanced statistical thing. And, that's not as obvious in my vocabulary. But it's really a relatively simple thing. It's the distribution that measures the frequency of intervals between rare events. If we think rare event as being when you're going to die, okay, lifespans are especially if you assume a model of reincarnation, right? You're dead, then you come back to life, and you go through this again. You can now ask, what is the distribution of lives? Okay, each life is an interval between rare events. Does everybody see it? In the light bulb model, the reincarnation obviously holds, right? When the light bulb goes out, you put another one in. Okay? So what the Poisson distribution does is it measures the interval between rare events. And it says that the probability of surviving X days, okay, is going to be a function of the mean lifespan, which is mu, and the number of days that you live. So this is this weird-looking function here. Okay? Any questions?
So the lifespan distribution is a special case of Poisson?
Yeah, so Poisson distribution is a good way of modeling lifespans. Okay? It is, in some sense, it's related to this binomial distribution, as you've kind of said. But it's kind of measuring the distribution of the gaps of between events rather than the number of events. Okay? If you think about what the binomial distribution measured, it measured how many burnouts were there if we ran a certain number of experiments, right? This is going to be a little bit different. It's going to be telling us what is the distribution of gaps between burnouts. Okay? What's the likelihood we have gone a certain number of days without a burnout? Yeah.
So it's saying the size of the gap between rare events.
Right.
Not the number of gaps between rare events.
Right. It's telling you the frequency of intervals, meaning the size of the gap between rare events. Okay? Yes?
So can I say that is it possible for us to say that, say something as rare as a stock market crash follows a Poisson distribution, like, and can we get a frequency intervals between two stock market crashes?
What it is true is, what a distribution like this tells you is, if you assume that stock market crashes are Poisson, okay, then knowing how often there is a stock market, the average number of stock market crashes, tells you about how far apart they should be. Okay? So that's actually exactly what the power of this thing is. How often, do we know something about how often there are stock market crashes?
Once in 10 years.
You say once in 10 years. I would say we know it because if we took a look at, we have 100 years of stock market data, we define what a crash is. We could figure out exactly how many crashes are there per day, okay? Or equivalently, how many, and we could take a look at what was the observed, okay, what was the, if we knew that we had been looking for 100 years, and we saw 17 crashes, the average gap between crashes is going to be 100 divided by 17. Does everybody agree with that? So in this case, we would know what the probability, what the average interval is. That's all that you need to now know what's the probability that there is going to be a stock market crash, okay, of length, of length 17 days, since, an interval of 17 days between crashes. 96 days. What this does is, if you assume that the distribution is Poisson, the neat thing is it gives you if you know the expected interval between events, it lets you figure out what is the probability of there being an interval for any interval size. Okay? So what is the probability there's going to be a crash, within the next month? Okay? Is something that, given mu, okay, and given the assumption that it's Poisson, you can compute that. Okay? Yes?
This always works in the retrospective, right? Like, the event is rare, right? If we were able to, like, tell how often it's going to happen, wouldn't, like, we be able to model it more accurately? Like, so let's say you already know about the last 5 crashes, and then you are able to say, like, this was the mean time between them. But if we cannot really accurately tell, right, like what is going to be the next crash, it may be like way out of the range because
okay, so you're not going to predict the next crash, but you would like to be able to predict what's the likelihood there is going to be a crash every number of days from now into the future. Okay? Suppose we learn that on average there is a crash every 8 years. Okay? What is the distribution of crashes going to look like? If it was normally distributed, we knew what it was, right? But if instead there is a model where, if we knew that the crashes were being generated by this distribution, okay, this is a different distribution than normal, okay? And what I'm going to say is that for when you have Distributions where, okay, the process you're modeling is the gap between events, okay, a Poisson distribution tends to be the right distribution for that. Okay? Any questions about that? Okay? So again, if we think about light bulb crashes, actually I didn't have that here, but okay, if I wanted to model, and I think I have an example in the book, where if you wanted to model, you know, let's say you wanted to model how long light bulbs are going to last. You know in general that light bulbs will survive for on average of 1,000 hours or 1,000 flips, depending upon what we're dealing with. Okay? What is neat is if you model that as a Poisson distribution, now you know for any given number of hours what's the probability that the light bulb will actually last that number of hours. Okay? And that's a different level of knowledge than just knowing what's the probability we had a certain number of burnouts per 1,000. Okay? Which is what we would have gotten from the binomial analysis. Any questions about that? Okay? So, any questions about that? Okay? So, as an example of how I think the binomial distribution is interesting, how many kids does the average family have? In the United States, it's famous. How many kids does the average family have? 2.2, okay, is somehow what it is. Now, if you know that the average family has 2.2 kids, how many families are there going to be with 4 kids in it? Okay? Now, in order to answer that question, you have to make an assumption about what the distribution is. Does that kind of make sense? And you could say it's normally distributed, okay? But when I ask you why is that normally distributed, it's not clear to me that that actually is a normally distributed phenomenon. If we kind of view that there's a model where every day, okay, a family, you know, the kids start to act up, and they finally decide, the parents say, no more kids, okay? You could now imagine a world where, okay, there is kind of this rare event that on a given day, this is sort of independently at points, somewhere the bulb is going to flip, okay? At that point then, the Poisson distribution becomes a reasonable model from it. And I took a data here where I took a look on one of these things. The blue thing is the Poisson distribution of what is the probability of having X kids if, if the mean turns out to be 2.2. And Y is, and I also show the actual observed number of kids that I saw in a family data set. And the data fits it reasonably well. Okay? And so bottom line is, when again, if families are constantly deciding whether or not to have any more kids with a fixed probability of P, okay, if that's the model, then you would expect it to be fit the Poisson distribution. And in fact, the data seems to do a reasonably good job of doing it. Okay? So what's interesting about the Poisson distribution? It gives you a way to take a mean and project it to a distribution for all values that are in there. Any questions about that? Okay.
Whether we were dealing with like some gaps or intervals.
So it's the intervals between the family deciding, yes, I want kids, yes, I want to have kids. Every day they're flipping a coin, do I want to have kids, do I want to have kids? The moment it comes up to be no more kids. Then the family dies and is reincarnated, and they flip the coin. What's the probability of having, do I want to have kids? Do I want to have, no more kids? The family size is basically a function of how many coin flips were there before it came up no more kids. Does everybody see that? And if you assume that model, you may not like that model. But if you assume that model, you get a Poisson distribution. And what I want to say is that there's a lot of things in the world that fit this kind of model once you start to look for it. Okay? Any questions about that?
So any kind of binomial distribution where only half the distribution is there, that we should model as binomial?
Now, anytime that you're interested in what is the distribution of gaps between heads, that is what the Poisson is measuring. What is the distribution of the length of the gap, the gap size between heads? Okay? And if you model something like that, the Poisson distribution covers it. Any questions about that? Okay. The final distribution I want to talk about today, okay, is the power law distribution, which we've mentioned in here a couple of times. And maybe this is something that, you know, growing up with data on the web and things like that, you're kind of more familiar with. Okay, but basically what a power law is it says that the probability of x is going to be x raised to the minus a for some exponent a. And let's think what that actually means. Okay? It means that as x gets bigger, what is happening to the probability of x happening? Suppose we know that the probability, let's write that out with the right thing here. If we're saying that it's the probability of x is going to be equal to c times x to the minus a, okay? If as x goes up, what is happening to the probability? It decreases exponentially. Does everybody see that? So suppose we think that this is the probability distribution for wealth. What does it mean? As I double my wealth, the probability of me achieving that wealth goes down substantially. Does everybody see that? So what's interesting about power law distributions is that they don't cluster around a mean, okay? The smallest value is always going to, get, be in some sense the most frequent. And then as we move further away, though, although it decreases exponentially, it doesn't really fade away. Notice that the tails for a power law distribution are larger in some sense than they are for a normal distribution. Okay? If you think about it, what is what is the normal, what is the average wealth in the United States? Somebody give me a number. $50,000. Okay, we can quibble about that number. And what do we think the standard deviation of that would be if this was a bell-shaped curve? Okay? If we think about it, if it was a bell-shaped curve, 2/3 of the population should be within one standard deviation of it. What would be the standard deviation? What would be the value? How much would you have to add to this till you capture 2/3 of the population? You want to say $25,000. That's $75,000 is 1 sigma, right? 2 sigma would be, according to that, 100K, right? Where is Bill Gates on this? Not very, very far away. But in terms of standard deviations, how far is Bill Gates away?
10, 11.
Not 10 to 11. Bill Gates' wealth is what? 100 billion? How many standard deviations is that? Somebody with a calculator. What's 100 billion divided by 25,000? Give it 100,000. Okay? It's so many standard deviations away that there can't possibly be a Bill Gates if wealth was normally distributed. Does everybody see that? Just like there can't possibly be a person who's 20 feet tall. Okay? But in power law worlds, this is certainly true. If you've got 1 billion people, how many people lie 100 standard deviations from the mean? Well, you can compute what the probability is of lying 100 standard deviations of a mean. But it doesn't go to 0 that fast as you get further out. Okay? So power laws exist when you have a world where it's not really a bell-shaped thing, and very large values are rare, but do occur consistently. Okay? Any questions? Power law rules are kind of the 80-20 rules of the world. The 80-20 rule is sort of that says that 20% of the wealth is held by 80% of the wealth is held by 20% of the people, right? That's the kind of a rule that gives you a power law. Yeah?
In this case, in normal distribution and power law distribution giving me a different perception of the same thing. Like if I have to plot the wealth of United States, the normal distribution tells me that Bill Gates is very far away. And hence
No. So what it means is the difference is if we assume things are normally distributed, we can make a guess about how rare it is that somebody is going to have a certain level of wealth, right? If we had assumed that there was a normal distribution on wealth, then we would expect it to look like this, right? You gave me the mean and the standard deviation. You told me what it looked like, right? That was your assumption. If I showed you what the real probability distribution for wealth was, it would look like this. And it wouldn't really be normal, okay? In fact, the power law happens to fit that model better, okay? So recognize that when we give it a theoretical distribution, we're saying that, oh, the data fits this. And you can't say, how can the data fit both a normal distribution and a power law distribution? Presumably it can't. It fits one better than the other, okay? And understanding whether your stuff is power law distributed or normally distributed makes a difference. Any questions? Okay. So what about city populations in the United States? Let's say in the United States. Is this something that we would expect city populations to be normally distributed? Or do we expect that there are bigger outliers than you would expect from a normal distribution? Okay? Turns out in the United States, the average large city, when they define large as maybe above 100,000 people, is 165,000 people. If you figure out what the standard deviation of that is, you end up getting a huge standard deviation relative to the mean, which is a sign that there's a lot of problem. But if you figure that you're within three standard, there's only about 100 or so big cities in the United States, then you figure that, well, all of them should lie within two standard deviations of the mean. That would be an argument that the largest city in the United States should look like Indianapolis. But New York City has 8 million people. Okay, New York City is much more of an outlier than what you would get if cities were normally distributed. Okay? And that's because cities are not normally distributed. Does anybody want to live? Why do people live in New York?
Jobs.
Say jobs? That's not why they live in.
Better quality of life.
Better quality of life? Why do people move to New York? Okay, you say it's jobs, it's better quality of life. That's not what I'm going to say the reason is. What explains why there are jobs? Because there's a lot of people there. That's kind of the difference here. Does everybody kind of see that the reason New York is bigger than it should be is because things like jobs tend to accumulate. There's more people there, more opportunity to create jobs. There's more. If you want to start something, you go to where the big city is, right? You are more likely to end up at a bigger city as a function of how big it is. That's kind of what I'm going to be saying here, right? Stony Brook is a small city. Is there any reason for anybody to come here? They're not okay, but what I do claim here is that power laws will arise whenever you have a process where rich people get richer. Rich things, the things that have the most, are more likely to recruit something next. So why is it that wealth is power law distributed? It's easier to make money if you have a lot of money. Why is that? Okay, well, probably they get better advice. Probably if you want to pitch your startup, do you pitch your startup to Bill Gates or do you pitch it to Skiena? Okay? There's various processes in the world where if you have more money, it's more likely that additional money and opportunities will accrue to you, right? And that kind of unfairness is what causes power laws to arrive. Any questions? Okay. And again, that's basically kind of what okay. So that's kind of what, okay, any questions about that? Again, this is, by the way, a plot of city populations by rank. Okay, if you look over here, the x-axis is what is the population, is the I, and the y-axis is what is the population of a city. So this is showing what is the population of the 300th biggest city, U.S. city, the 250th biggest city in the world, right? Now it looks kind of, does this look normal? Maybe. Except notice a couple things. Notice that the numbers 1 through 5 don't appear here, right? In order to make this visible, I had to delete New York. I had to delete Los Angeles. I had to delete the other big cities. Does everybody see that? Because there's a small probability of much bigger elements. Okay? Any questions? So the other reflection of this is that if you take your frequency data and plot it on a log-log plot, here if we plot the log of the I against the log of the population of the ith largest city, this is now the distribution that you get. Okay? One thing that characterizes power laws is that they appear as straight lines on log-log plots. Okay? So if you want to say, when is my data power law distributed, this is kind of the initial test to see whether your data might observe that kind of a law. Any questions about that? And again, as I was basically saying, in a power law, whenever you multiply the value by x, you divide the number of people with it by y. That's what this equation was saying, isn't it? If I double x, this is now going, instead of being x to the a, it's going to be 2x to the a, right? That's the same as 2 to the a times x to the a, right? 2 to the a is y. So whenever you have a distribution where, when you multiply the value by something, you divide the number of, the frequency of it by something else, that defines a power law, okay? And that ratio between x and y is really captured by this exponent a. Any questions about that? Okay? So again, it's kind of neat. If we know that we have a power law, okay, and if we know something about what that ratio is, we can guess how many people there are with how much wealth. Okay? Any questions? Okay. So when you see an equation like this, the power law distribution, again, it's c, a constant times x to the minus a. Okay? The a is the important thing. That's the exponent of this thing. There is a multiplicative constant times that thing. But that constant is not important. You know why that constant is there? If we really have a power law, if this is a probability distribution, then if we compute what is the probability that x is equal to a, big X is equal to little x for all little x, we need to have the property that if we sum this up over all possible x, that these probabilities come down to 1, sum to 1, right? So C is just some constant that has the property that, for any given exponent, brings that down to it. Okay? Any questions? The rate of this exponent is what values what's interesting in a power law. Okay, any questions? So power laws arise whenever things have kind of a, a rich get richer thing. Okay? For example, in internet nodes, the number of, let's say you wanted to measure what's the number of visitors to a web page. Okay? That turns out to be power law distributed. That there's a very, very small number of web pages that get a tremendous number of hits. There's a large number that get almost nobody looking at it, right? And when you plot these things, you get a power law. Where is the rich getting richer here? Why is that? Well, it's the more people who visit a website, the more they're going to tell other people about it, right? The richer that website will be, and the more they will advertise. Okay? They will find ways of crushing other ones or something like that. So whenever you have a rich get richer phenomena, you get a power law. Another example that we're going to look at in here, like book sales. Okay? You know, I have my algorithms book, and I like to monitor these things, okay? There is some book that's the bestseller that sells an unbelievable number of copies, right? What does the average book on Amazon sell? Nothing. They've got billions of books there, right? Okay? If you plot the number of sales of the most popular book, okay, you get a power law, okay? And why is that? And why does it, if you sell more, are you more likely to sell more because you've sold more?
Yes.
Why? Because someone is more likely to have read it and told somebody else, right? There's more likely to get a review. Once you've got enough sales, you're going to get a review, and that's going to sell more. There's some mechanism here that is generating it. It's not immediately obvious. You know, it's not just that it happens to fall on these curves. It's usually a mechanism that's causing it to happen. Any questions? Okay. I'm over here. Okay, I mean, you know, I'm better than some and worse than others. Okay. Any questions? Another famous example of a power law that is interesting is something called Zipf's law, which governs word frequencies. Okay? When you say, what is the frequency of the ith most commonly used word? Okay? So the word the is used more than of. It's used more than and. The x-axis here is the frequency of the word, where the word ranks in terms of use in sorted order. The y-axis here is the relative frequency. What fraction of the time is this word used over all words that are uttered? Okay? And Zipf's law states that the kth most popular word is used 1/k as often as the most popular word. So by Zipf's law, we would expect the second most popular word to be used half as much as the first most popular word. The word that's 10th most frequently used to be used 1/10. Does everybody see that? And every time you double it down the line, go from 20 to 40, you would expect that the frequency of use would get halved. Any questions about that? Zipf's law is a power law because basically when you go from a word of rank x to a word of rank 2x, that's sort of doubling the ranks, we would expect the frequency of use to go down by a half. Okay? Any question? It's a power law with the exponent a equals 1. Any questions? So knowing these things is kind of important because there's a lot of processes that follow these power laws. Okay? And recognizing when they are like, why would there be a power law associated with word frequency? Do we think that there's any reason why words that are used more often are more likely to be, you know, if we were to be used still more often?
There in the vocabulary, like there are some stop words like we use for every sentence.
Okay, so what we would kind of expect a little bit, at least as part of this phenomena, is that a word that starts being used a little bit is more likely to become, you know, the more people use a word, the more people know it, means the more that they can use it, right? How many of you have ever used the word defenestrate before?